let me make some comments and then open it up for questions. Number one, the Euler-Lagrange equations are second order in time derivatives. Okay, and therefore the solutions, the solutions are subject to boundary conditions, which you have to specify positions and velocities, right? Just as we know about Newton's equation, right? The other thing is that for more general systems, the position x of t, doesn't have to be, or the velocity x dot of t, they don't have to be the usual, within quotations, usual positions and velocities, okay? They can be more generalized things. So for example, if I look at a simple pendulum with a small oscillation, then the Lagrangian is, what is the kinetic energy? It's something like, I may get this wrong, but it's half, there is some, half theta squared, right? So I think there's some, I'm missing some factors to make this dimensionally correct. But what I'm saying is that for the simple pendulum, it's really the angular velocity, which is the kinetic energy, right? And then there's some constant times the potential energy has some cosine, which in some small approximation just gives me theta squared. So here we see that the position is the angular separation. If you have a simple pendulum, it's oscillating. This theta is the real variable, because superficially the simple pendulum looks like it's a two-dimensional system, but we know that because there's a constraint that it must be on a string, it's actually a one-dimensional system. And in the Lagrangian, all that the Lagrangian cares about is the potential kinetic energy minus the potential energy. And therefore, theta is a generalized position or generalized coordinate, okay? And theta, dot is some generalized velocity, okay? So this means that if I take a very complicated system, all I need to do is to actually write down the energy and the Lagrangian in terms of the degree of freedom that is the real degree of freedom, not the position in physical space. Okay, so comment number 3 is that it's easy to generalize to many degrees of freedom. So for many degrees of freedom, the derivation that I just gave, the Lagrangian is just going to be given by sum over all the particles or degrees of freedom. So Qi are the positions. So these are the kinetic terms. And then sum O and the potential. And the potential can involve the interaction between different particles, right? So this can contain a lot of interaction. So for example, a very common exercise to do is like they give you a system of like the double pendulum. So you have a pendulum at the end of a master's rod, another pendulum, attached to the first pendulum, and it's if you were to use x's and y's, this would look very, very complicated. But if you use just the angle theta here, theta 1, and the angle theta 2, then it's a lot easier. Okay. So these are my comments. So I think it's a good point to have discuss some questions.
I wanted to kind of make a comment on Nahi's question. I think what he was really asking is whether or not the particle has like local information or global information about.
Yeah, that's a good question. Yeah. So in classical mechanics, it actually has only local information, and you can show that if you take Tf to be T initial, T0 plus delta T, then the Lagrangian, that's basically just a principle of least action is nothing but the Lagrange equation. Okay. So it only has local information in classical mechanics, but in quantum mechanics, it has more global information.
Could you make some short comments on how that can be possible?
Yeah, I mean, ask God would be one way of saying, but the other way of saying is that suppose that in quantum mechanics you have the double slit experiment, right?
Yes.
And the double slit experiment can be described in terms of quantum particles, and so there is some probability that the particle starts from here at x0 at t0 and finds itself over here, say at xf at tf, right? Or x at tf. Sorry, it's a redundant notation, but so what quantum mechanics tells you is that what is the probability that the particle starting here will end up here, and that amplitude is called xt0 xtf, right? Now, what Feynman showed was that this amplitude, which you use, so the square of this amplitude will actually give you the probability. This amplitude basically says that to compute this amplitude, you sum over all the paths that connect this point to this point, but each path has to be weighted by exponential times I, a phase factor exponential times I, the action evaluated on that path. So in the double slit experiment, there are essentially two paths possible. This path and this path. Okay? And you can calculate these actions very easily, and you find that, yes, that's true. It gives you the correct amplitude. Now, the thing is that, if these are electrons, you can let the electron intensity to be very, very low, such that at any point, there's only one electron in the experiment. So to look at the probability amplitude, probability that's related to this, you have to, this is the square of this. You have to send a lot of electrons through, right? And you find that at the end of your experiments, the probability, the intensity distribution is like this, which is typical of two slits. So for each quantum particle, because the intensity is so low that at any point, there's only one particle in the apparatus, in the experiment. So that particle, does it go through this slit or this slit? Tell me, Nahi.
Sorry?
that particle, does it go through this slit or this slit? What do you think?
Well, quantum mechanically, it probably won't make sense to say one of those.
Exactly. It smells both slits. It goes through both. Otherwise, how can we have this interference pattern if there's only one particle in the apparatus at any given time?
Yeah.
So that is how classically, it only knows about one path, but quantum mechanically it knows all the paths. Okay. This is very, very strange. I mean, if you're not shocked by this, then there's something wrong with you. Well, I find it's rather shocking. Any other questions? You don't have to be shocked by this. Maybe you're a new generation. You grew up with TikTok and stuff like that. Maybe you're not shocked by anything. Any more questions? Okay, so before I move on, let me just do another round of attendance. So is Afia here? No. Moon is here, I see. Nusaiba, are you here? And Nahi is here. Nian, are you here?
Yes, sir.
Okay, good. Farhan? Oishik? Okay. All right. So if there are no more questions, let me move on to the Hamiltonian formulation. So let me just summarize the Lagrangian formulation. So a Lagrangian, say, of a many particle system is its kinetic energy. So it'll be a sum of half times m, its generalized velocities, and then minus the potential, and the potential could be, it should be a sum of all the QIs, and there could be interaction terms. Then the principle of least action. So this is the action. So the principle of least action says that for the physical path, the variation of S needs to be 0. And that physical path then satisfies what is known as the Euler-Lagrange equation, which is this complicated looking equation, but actually it's not. The Euler-Lagrange equation. So this is the Euler-Lagrange equation. So this is what physicists did between Newton and Maxwell. Between Newton's discovery and Maxwell's discovery, not much happened in physics in terms of fundamental discovery laws of, well, also, of course, there was like electricity, but apart from that. But people reformulated Newton's law in more and more sophisticated forms. And that became very, very helpful later.